Now I start the also recording. Uh, so I'm not going to use the second camera today. We will see how difficult it would be for me to write all those equations on the pad. Okay, so this is a kind of experiment we are going to face with. Now I'm going to upload. For last week, we have seen that there are similarities between electrical systems and mechanical systems. There are two types of motion. One of them is rotational motion. The other one is a linear motion or translational, they call it generally. For both systems, if you have a mass which is equivalent, there is an equivalent electrical part as well. And the equation simply would be mass times the position double dot. Double dot means the second order derivative of it, plus b. We have already seen that, and today we are going to see this one as well. This is that is the material you are going to see now. And now we might have, you remember that, we might have the friction, or we might have kind of sorry, spring. Follow my cursor, please. Spring action, or you might have friction as well. Those spring systems might be connected series like this, or parallel, or if it is connected like this one is a friction, then friction might be parallel or series connected. Okay, so in order to obtain the equivalent of it, so we need equivalent. Let me look at this one for example. K equivalent is required, and that one for K equivalent required. For this one is of course B equivalent. For both of them are required. So we have to look at those. In order to do that, I'm going to open up a piece of white paper, and I'm going to derive those equations for you. It's going to be difficult for me. I'm going to test it whether I could continue on this manner or not. Okay, so I open a white paper now. Now you can see that a white paper, piece of paper here, and now we are going to look at for that one. Sorry. don't want to write 5. Okay, I'm going to write 1 punto small. We'll see whether you conceive properly. So the system is this. System is this. And the force here is applied to this system. That one is K1. That one is K1. K1. That one is K2. Puntoyu biraz kalınlaştırayım çocuklar. Çok silik geldi bana. Can you see it properly? I don't know. I'm going to, which one is better? Now, if I write equation for this one, this and this position here is x. Okay, so the equation is simply would be follow me please, k1 times x plus k2 times x. The same x is, the position is the same for both of them, is applied, which is equal to f, which is equal to K equivalent times x. From this point, K equivalent can be obtained as K1 plus K2. However, for that kind of application, that's, by the way, is a reference frame. So actually force is, there are two rubber material, for example, which has a which has the position changing or energy storing capability. And if you have, those are parallel connected. For this example, by the way, we have R1 and R2, and the same force applied. However, that position is Y, and that position is X. So that is K1, that's K2. Then if you write the equation here, K1 times Y is equal F. Same F is affecting those, and K2 times X is equal to F. Is it correct? I'm just checking up whether you are following me or not. What is affecting that? What is affecting that K2? The one position is X, the other position is Y. Therefore, K2 times X is wrong. K2 times X minus Y equal F is a correct one. So if we derive here K1 times we derive y here from this, the second part. You can't see the cursor, so I have to show the cursor. So if you take the y here and put it there, the y, then you are going to obtain k1 times I'm sorry, I have to clean that one. It's not k1, that's k2. So k2 times x minus, so we, instead of y here, what we put here, you can see that instead of y, we write f over k1 which is equal to f. If you solve it, you are going to obtain that k equivalent is equal f over x which is equal to k1 k2 over k1 plus k2. Now I'm asking a question to you. Is it similar to the parallel connected, is similar to capacitance, isn't it? Similar parallel connection or series connection capacitors. If those capacitors are seriously parallel connected, then of course you are going to obtain the equivalent K is something like this. Equivalent K is something like that, and that is the equivalent K for that part. Similarly, that could be done for parallel and series connected resistance. So we have to go back, since it's already recorded, so this picture is going to remain in your file while you are studying. So I'm going to open up a new one. Now this is the point. Sorry. Kalemi açmak lazım. So that is the point. And this point is connected since you have that slide. So although the figure is not very good, doesn't matter. That point is x, that point is y. For that kind of connection, this one, that one is B1, this one is B2. So two viscous friction or resistance damper are parallel connected. For that case, we are going to write the equation F, which is applied to the point Y. F is equal B times, sorry, B1 times Y dot minus X dot plus B2 times Y dot minus X dot. Then of course, a force is equal to B equivalent times, sorry, Y dot beğenmedim. Sileyim burayı bir dakika. B equivalent times who is going to help me to write the equation here? Assuming B1 and B2 are parallel connected here, you can see that B1 and B2 are parallel connected. In that case, what is the equivalent? Since this position is X and this position is Y, so between those Y and X is affecting, Y is output, so output dot Y dot minus X dot. From that point, B equivalent is obtained as B1 plus B2. On the other hand, for series connection, I'm not going to draw ya da çizeyim. This point is Y, this point is Z, and this point is X. This is B1, that one is B1, that one is B2. If you derive those equations, you are going to find that I'm going to give you the result. B equivalent is equal to B1 B2 over B1 plus B2. So these are the equations at the end we can use if it is necessary. Okay, so I'm going to come back to original slide. the original slide, we know how to calculate the equivalent K values if those are parallel connected or series connected and things like this. If you have a problem like this, how could you solve it? You see, there's a car here and there's another car here. So this car is movable inside this car, and that car is also moving on the reference frame. That is the reference frame. So we are going to solve that mechanical problem. We know that that position is here U, biraz büyüteyim bir dakika. That position is U, and that is X. I'm going to open the relevant document. I'm going to give hint first. How could we solve? How could we obtain this one? I'm going to read the problem. Let us obtain the mathematical model of this system by assuming that the cart is standing still for time smaller than 0, and the spring mass dashboard system on the cart is also standing still at time. So system is stand still time at the beginning of the time. In this system, ut is the displacement of the cart. As I told you before, that one is ut. So in order to understand the problem is important. Ut here, that one is the displacement of the cart, position of the cart, and the input to the system at time equals 0. The cart is moved at a constant speed of u dot constant. Şimdi buraya vaz edelim bunu. Bir dakika. U dot is constant. Bu niye küçüldü böyle ya? Allah Allah. Bu speed bu. If the car is moving with a constant speed, what's going to happen? Displacement yt, hangisi yt? The second car of the mass is the output. So y is the output. Tamam. Şimdi gelelim buraya. Evet. U is the input, y is the output. So how could we solve this equation? Now what we are going to write, total mass times A is equal to F. Is equal to F. Whatever the F is available is that one. So I write the equation here on top of this one. Then I'm going to come back to clean page. Now, M times sorry. So I write the equation here. Right. M times Y double dot plus B times Y is our reference. Y dot minus X dot. Sorry. Y minus U dot. U is the position of it's not used X. U dot plus K times you help me, I couldn't write. Who is going to tell me? What am I going to write? Can't you write? Çocuklar bakın bunu öğrenmeniz lazım. You have to learn this. So for K times the position of this one is Y, position of that one is U. So that means the reference is this one. So that means Y minus, bu niye böyle büyüyor ya? Allah kahretsin bunu. Tamam. Y minus X. Sorry, U. Is there any different force defined? Dışarıdan bir kuvvet konmuş mu? No. Therefore, it's equal to 0. This is a system dynamics. while system is moving with a constant speed. So this u dot is constant. So what's going on then? I'm going to continue in a clean page, but you just remember the second car position is reference and y, and the first car's position is u, and the speed is constant. Okay, this is the condition. So I go back to a new page. So if I continue the same equation, m double dot plus b times y dot plus k times y is equal to b u dot plus k times u. Then the equation becomes, now what are we going to do is the time domain. This is a time domain. Time domain equation. Okay. Now what are we going to do? We are going to come back to S domain. Now you help me to write the S domain. Who's going to write the S domain? Check yourself whether you cannot write the S domain equation here. That means you are not going to pass this course. So you have to become the controller of yourself. So you have to be careful. We all said that derivation means S. The second derivative is S square. So what we are going to write here, m s square ys plus b s ys plus k ys, sorry, ys is equal b times s plus k us. Bunda ys parantezini alırsanız m s square plus bs plus k bracket ys is equal bs plus K US. So what's happening here? YS over, what is the transfer function? The transfer function is the function of the car over US. So YS over US, TF transfer function. So equal YS over US. So that means TF is equal to BS plus K over MS square, MS square plus BS plus K. This is our transfer function. This is our transfer function. What do you think about the transfer function? We have 1, 0. 0 is equal minus K over B. And we have two poles. Of course, the location of those poles are defined by the value of M, B, and K. Okay? Your mind is going to be widen up as long as we discuss those poles, the location of those poles and zeros. Okay? Let's continue now. Now we have already seen this problem. We have already solved it. And now we are going to solve this problem. This is going to be a little bit longer, of course, than this. I'm sorry, not this problem. That problem. How do you solve this problem? It is only 9:45 and you are reminding me the break. Can you solve this problem? There are two reference frames, and there are two cars, and the cars position, one of the position of the car is x1, and the other position of the car is x2, and these two cars are connected between those with a friction and spring, and each car is connected to system with spring to reference frame. One of them is K1, the other one is K3 olması lazım. That's right, K3. So that is the problem. And it is expected that we have to write down the equations, mechanical equations, and obtain the transfer function. O transfer function'ı bir tanımlayayım bakayım. X2 over US. U here is a force. Be careful. Is not position. U is a force. Bunu yazayım buraya ben. Çünkü öğrenci, generally speaking, the students learn the one example we have. You said it was a position, but this time is force. Ben bunu çocuklar force için çözeceğim, tamam mı? Bunu F yapıyorum. U yapmıyorum. F için çözeceğim. I'm going to solve it for force. Okay? So let's write the equation first here. Basit bir denklem yazalım buraya ya. Şurada yer var. Çünkü if I don't write the equation here, you are not going to understand what's going on. The first equation, biraz küçülteyim şunu. Punto 5 punto çok büyük geliyor. 2 punto, evet. Now I'm going to write the equation and then you are going to help me. Tamam mı? Yardım ediyorsunuz bana. You help me. Şimdi hangisi için yazalım? What's the transfer function is expected? X2 over US. Şimdi şuraya onu da yazayım. X2 X2 over US TF'tir. Transfer function. Tamam mı? Is expected to obtain that one. What are we going to do? First, I'm going to write the equations here. The first one for M1. M1 times X1 double dot plus İniyorum aşağıya, resmi görmek istiyorum. I would like to see. B is defined between two positions. So since it's X1 is our reference, X1 minus x2 dot, of course, dot başka ne var? Plus k1 x1 plus k2 x1 minus x2 eşittir equal, what's that one? Is it 0? I ask you a question. Who is going to answer? Are you listening me? Are you with me? Okay. Amin says it's equal to F. Is she right? Amin, you are a lady, aren't you? Or man, or boy? You are a girl or boy? Oh, I'm sorry. I'm sorry. Amin says it's F. Is he right? Okay, I'm not going to spend time. Thank you, Amin. Is equal to F. This force is actually defining all the mechanical stored. That is, for example, this one is a stored energy. This one is dissipated part. That these are also represent stored energy. It's a spring action. Is all supplied by F. So this is one famous equation you can write. The second equation we are going to write, I'm going to write it here since it's going to be easy for us to follow. Şu force'u siliyorum buradan. The second equation for mass 2, okay? Let's write it again together. Mass 2 times x2 double dot oh no, oh no, there's something happened. I don't know what happened. Anyway. Buradan devam edeceğim. Bakalım yazabilecek miyim kalemle yalnız. Yazamazsam çok kötü olacak. Evet, yazacağım gibi. Şimdi devam ediyorum. M2 times X2 double dot plus B times, then our mass is M2 is our reference, therefore X2 minus X1. O aferin, aferin Amin. X1. Then plus K3 X2 plus K2 bracket X2 minus X1 is equal to force. Is it correct? It is not correct, since there is no force exerting on this one. Is this force, the initial force, is just transferred to this part. So we are not going to have write a force here is equal to 0. Is equal to 0. Sorry. Is equal to 0. Okay. All right. So if we continue in that manner, I'm going to write the equations a bit fast then for a clean page. Okay. M1 X1 double dot plus B1, sorry, B bir tane. Burada silmek için bayağı bir uğraşıyoruz. Sonra silgiye gidiyorum. Silgiyi tepesinde dolaştırıyorum, siliyorum. Ondan sonra kaleme geri dönüyorum. I come back to the pen. Okay. B times X2 dot plus K1 plus K2 times X1 equal to B times X2 dot plus Allah Allah. Can you see this? I don't know. I don't know what's going on here. That's the size I'm using. Plus K2 times X2 plus force. This is the first equation. The second equation, M2 times x to double dot plus b times x2 dot. Burada bir yanlış yapmışım. O yanlışımı gördüm. Bu bir bu. bx2 dot plus k2 plus k3 times x2, which is equal to b times x1 dot plus k2 times x1. There's no force here. So if you write those equations in S domain, color değiştireyim de biraz şey olsun. In S domain, M1 S square plus BS plus K1 plus K2. Allah. S1x is equal to BS. As far as dot is concerned, when you come back to S domain, you use S plus K2 times X2 plus F. Okay. This is the first equation. Second equation, M2 S square plus BS plus K2 plus K3 X2S which is equal to BS plus K2 times X1. So what are you going to do now? You are going to take X1 from here, then you put it here and you solve it. Then you are going to obtain the transfer function, which is equal to, I repeat, we have two equations. Bir kontrol edeyim denklemleri çocuklar yine de. M1 S square plus BS plus K1 plus K2 times X1S is equal BS times K2 times X2S plus US plus FS. Pardon, F'i de böyle bırakmayayım. Doğru. Yerde kalmamış ama şunları sileyim, doğru düz yazayım şunu. Notlarınızda kalsın. Şunu da sileyim, biraz yaklaştırayım. X2S yapayım. Tamam. plus fs. Tamam, şimdi oldu. Güzel olmadı ama o doğru. Bu ikinci denklemde I'm going to check it up. M2 times S square plus BS plus K2 plus K3 X2S equal BS plus K2 X1S. Right. Now what are we going to do? We are going to pick X1S, for example, here, put it there. Follow my arrow, please. We are going to get the X1S here and put it there, and then sort it out and obtain the x2. That equation is equal x2 over fs. So the result is going to be, bize ne lazımdı? x1 over x2 over, şekle bir geri dönelim bakalım. Şekilde, evet, bize x2 over fs lazımdı. O zaman ben hemen yazıyorum buraya. Bunu da kırmızıyla yazayım. Rahatça ayırt edin. x2 s over fs force eşittir bs plus k. Allah, bıktım bundan ya. Niye değiştiriyor acaba? Kendi kendine değiştiriyor. BS plus K2 over M1 X, sorry, M1 times S square plus BS plus K1 plus K2 times M2 S square plus BS plus K2 plus K3 plus, sorry, minus BS plus K2 evet. Burayı tabii silmek zorunda kalıyoruz. Bu S de olmamış burada. Bs minus Bs plus K2 karesi is obtained. I'm tired too, so we are going to take a break. Is it all right? I come back to the figure and then original figure. Where is this? Yes, we have solved this problem. Okay, and we obtain the motion of the second car here, M2. You can also obtain the first car's motion as well, motion equation. We obtain the transfer function, how much motion is going to be obtained but when solving those equations. Okay, now we are taking a break at 13 25 10:25. Okay, see you then. Hello again. Now another example is this one. For this one, it's going to be easy for us. So we are all electric people. So I'm going to write the equations here first. Then I'm going to come back to the white paper. Okay. So let's start. What we need, we are going to require to obtain E O S over E I S. Okay, this is what required. This is what transfer function is all about. Output divided by input. So the easy equation is this. There are two equations by the way. One of them, şu şeyi biraz incelteyim kalemi. One of the equation is this. EO, şuraya yazayım. EO is equal to, output voltage is equal to 1 over C integral I dt. Okay, this is one equation. The other equation, the current is flowing. You can see that current is flowing here, which is I. Okay, then the other equation is equal L di dt plus Ri plus 1 over C I dt, which is equal to EI. Sorry, EO, output. Then if we write from, I think I have to go to the clean page. Okay, there is no room for me. Now, since EO was equal to 1 over C integral I dt, then EO dot is equal to I over C. Or in other words, I is equal to C times E O dot. Okay. So this is one group. From that one, di dt is equal to C times E double C times double dot. So I get the derivative of this one. So this one. Then if you come to our original equation, L di dt, original equation was this one. L di dt plus Ri plus EO plus EO, which is equal to, sorry, EI. That was our original equation. So di dt is equal C double dot. So L C E O double dot plus RC I here C E O. Allah Allah. Hiç olmazdı böyle bir şey ya. E O dot plus EO is equal EI. So if you come back to S domain, L C S square plus R C S plus 1 times EO S is equal EIS. So transfer function becomes EIS over EOS is equal to 1 over S square, sorry, LC S square plus RCS plus 1. Is it all right? We have obtained the transfer function. We have seen that we have two poles in our system. It's a second order system. I'm going to write that one in a different form. Just clean the, sorry about, sorry. EO over EI was equal to 1 over LC, Allah kahretsin. LCS square plus RCS plus 1. In other words, 1 over LC over S square plus R over L S plus 1 over LC, which is equal to omega n square over S square plus 2 zeta omega n S plus omega n square, which is a very famous second order system response of an electric circuit, LCR circuit. Omega n is the resonance frequency. So omega n is equal karekök 1 over LC. Zeta is a damping factor. Therefore, zeta is a damping. So it's a typical second order system. So şu S'i biraz düzelteyim. Kopyada doğru düz görünsün. Şu C pardon, S değil. We obtained the transfer function of the LCR network, okay? Oh. Now we continue the next slide, next example. This is going to be a circuit. Two LC circuits are connected like this. you are going to prove that you are going to prove that for this one you are going to obtain rather TF is equal EOS over output over EIS. Homework. You are going to obtain that one, okay? However, if you have a system like this, it's that easy. For a system like that, it's that easy. The transfer function of this one, you know what is RC? For RC, the first part, I'm going to write here. For the first part, we have the transfer function is equal to bir dakika kalemi açayım. For the first part, for this one, TF is equal to 1 over R1 C1S plus 1. However, for this part, transfer function is this. Bakayım yer var mı yukarıda? Tamam, var. TF1 diyelim buna. This is TF1. That one is TF1. TF2 Allah ben anlamadım. Niye bu böyle olmuyordu eskiden ya? TF2 is equal to 1 over R2 S2 S plus 1 plus 1. So what is happening here actually the total transfer function would be buraya yazabileceğim gibi görünüyor. EOS over EIS is equal to K divided by the first one R1 C1 S plus 1 times R2 C2 S plus 1. So this proves that if you have another equation or another system between these two RC networks, is you simply you can calculate the first transfer function of this one, then calculate the second transfer function and multiply with k. That's all. The gain of the isolating amplifier network, whatever it is. So this is the principle of whether there is an amplifier like this between those buffer. But this network, which you are going to derive those equations, and you are going to see that it's not going to be like this. Okay. In the meantime, I'm going to give those home assignments to O'Learn system. Then you are going to solve it and send it to there. Okay. Yes, the mechanical model of a vehicle. Actually, this is called, that one is here, is called a bicycle model. Actually, there are other tires as well. So there are 4 tires. But if you consider only 2 tires, it's called bicycle model. So you can only see that effect. If you look at to me, that effect, you are not going to see this effect. Only it's called pitch effect. I told you before, pitching effect. So, however, for even that one is difficult to write the equations since there is a center of gravity here somewhere there, and you have to write those equations for that one. Instead, we use this model. This is a single tire model, single wheel model. Okay, where we have a suspension system here, and also the friction here. Of course, that is the position of the ground, all right, and that is the body of the. So any person sits inside the car will see the position change of, görünmüyor, büyüteyim biraz. X output is the body, okay, but it's a single tire. Otherwise, if we take 2 tires together, then it's going to be if you look at to me, it's going to be a motion like this. We have to take that one. It's going to be difficult. But for mechanical engineering world or automotive engineering world, 4 wheels are taken into account. So of course, a lot of equations involved. For this one, it's simple, isn't it, to write those equations? Şu modeli bir daha çizeceğim herhalde. Buradan kopyalayamıyorum herhalde. Evet. Şimdi temiz bir sayfa açıyoruz. Single tire model. Bir tane denklem buraya ben yazı versem fena olmayacak. Bir dakika. Yazıyorum şuraya. Biraz küçültelim. 2 ponto, tamam, yeterli. Mass times x o double dot plus b times xo minus xi dots. So that means m d square xo dt plus b dxo dt minus b dxi dt plus k times xo minus xi. There is no additional force, therefore it's equal to 0. So that is the equation we have. Okay, as long as we write the equation, so we are going to put the first part and second part. I'm going to continue in a new pad, new page. The system has got a mass, vehicle body. This is the mass, and there is a friction. Sorry, there is a spring and friction action. B. This is the road. Which position of that one is x1? Sorry, x input, and that one xo. So the first equation we have written was we have done it. So I'm going to write continue m x o double dot plus b x o dot plus k x o is equal to bx input dot plus kxi. I'm sorry, dot yok burada. I made a mistake. All right, kx. So result, so if I come back to S domain, m s square plus bs plus k times xo s is equal to bs plus k times xi. xi. So transfer function then obviously is easy now. Output divided by input. X output over X output S over X input S transfer function is equal to BS S olmadı. BS plus K over M S square plus BS plus K is obtained. So this is a simple model. There is another example. I'm going to do it for you. Is it clear? This is very easy problem. That one is the position of the road, and that one is the position of the body of the vehicle. So the person who is sitting in the car has got that kind of let's say change in the position. Their seat will change its position with any change in xi is going to cause that kind of change. So XOS, for example, might be calculated from this. Şuraya yazayım. XOS is equal to TF times X IS. This one is transfer function, TF. Okay, so you can obtain any position change in the vehicle. If you have the change in the position on the road, you can obtain that one. Okay. S-domain equations are easy to solve, but don't forget that the real life is in time domain. Therefore, you have to come back to time domain from those equations. Let's see another example. What's going to happen if we have a system like this? I just read the problem here. By the way, if you have download the Ogata's book, there are a lot of solved problems in it. This is one of them. Obtain the transfer function of ys over us of the system shown in figure. The input u is a displacement input. Displacement, unutmayın, force değil. It's not a force. This is also a simplified version of an automobile or motorcycle suspension system. Of course. Now, what's the difference between the one we have solved and this one? Who is going to interpret that one? What is that one here? Hadi bekliyorum. Burada bakın bu yok. There isn't any, this one. What's that one here? Bir yorum yapan yok mu ya? İçeride kaç? 18, 17, 18, 17 öğrenci var. We have 17 students. What's that one? Ben Amin'den biraz ümitliydim. I'm expecting Amin. Think about this. What could be done? Right has got microphone open. Is it? All right, I come back. I do it. I answer. Now, if you look at here, that suspension system is here. Is actually suspension system is this one. Okay, here. However, what about tire? Tire itself is a kind of spring action. That one is representing the tire, and the road position is giving as if it's a sine function or something like this. How could you obtain the transfer function? It's easy. It's easy. You can write the equations easily. I'm just going to draw. I'm going to write the equations, and then you will follow me. Let's make it a bit fast. Puntoyu küçültelim. Let's make the okay. M1, the body of this one, that one is tire. Tire. Okay. That one is car, body. Ama yer kalmadı burada yazacak şimdi ya. Ne yapacağız? Şuraya yazma yok, yetmez. Ayrı bir sayfa açıyorum. So if you remember the model, o zaman da şeyi kaybediyoruz. Neyse bakalım da. Yeni sayfa. New page. System is something like this. We have one mass here. Then we have another mass here, which is tire. This is body, and this one B, and that one here, and the road. This one is road. Road is not simply like this, it's changing. Road is changing. Okay, it's not flat. This is K. Pardon. Bunu küçülteyim ben ya. Bir dakika. That one is K2. K2. That one is K1. This is M1. M1. That one is M2. And that one is B. So if you write the equation easily, you help me if I make a mistake. M1 times the position of, bir dakika, positionları da yazalım. Position of this one is Y. Position of this X. And the road is U. Position of the road is U. I'm sorry. So M1 times bir dakika. Hocam ben bunu değiştireceğim ya. Neyse değiştirmiyorum artık hadi. Kitaptaki örneğe aynen sadık kaldım. M1 times pardon. Bu M2 çocuklar, bu M2, bu M1. Lanet. Lanet, lanet. Bu M2, bu M1. Bu M1. Yazıyorum. M1 times X double dot plus B times X minus Y plus K K1 mı K2 mu ya? Eyvah bu da K2'ymuş. Bu K1'mış. K1 bu K2. Oh. So K2 times X minus Y. is equal to m1 times x. Bir dakika. m1 times x. Olmadı. Siliyorum. Şurayı siliyorum. Evet, doğru yazmışım aslında. Bir daha yazacağım şimdi. I'm going to write it again. K2 times x minus y free body diagram. Ondan sonra bunlara datları koymamışız. Şunlara da datları koyalım. Put dots. All right. K2 times and de plus K1 times position of the road is u here. So x minus u. Eşittir 0. For the second mass, m2 times y double dot plus b times y dot minus x dot başka bir şey var mı burada? Ha, k var bir de plus k2 times y minus x. Which is equal to 0. From those equations, you are going to obtain that when you solve those, okay, you are going to obtain that ys over us equal to k1 times bs plus k2 over, bu bayağı uzun. Şu taraftan iyice başlayayım. m1 m2 s power 4 plus m1 plus m2 times b s to power 3 plus k times k1 times m2 plus m1 times m2 plus m1 plus m2 k2 s square. Bir tane daha terim var burada. K1 BS plus K1 K2. Gördüğünüz gibi it's rather difficult to solve those since there are a lot of second derivation and first derivation involves. But at the end, it seems that the system like this, for one wheel only, the system like this has got a transfer function. You are sitting in your car and your car is U nerede? Burada. U da aşağıda. Your car is transfer function is this. Now I have a question now. I have a question to you. Bir önceki sayfaya döneceğim. Orada bir soru soracağım. I'm going to come back. So I'm just reviewing the slides. We started with the springs parallel or series, also the dampers or the friction parallel or series. We have solved this problem. We have solved this problem. We have solved this problem. We have also, this is your homework. We are going to solve it. We have solved and see that if there's a buffer between two primary and secondary networks, you just multiply with k, the transfer function of the first one, and the transfer function of the second one with multiply with k. And then we have seen this model. This model is simplified, considering the neglecting the mass of the wheel and also the spring action of the wheel. Spring action means rubber of the tire. There's air in it, pressurized air in it. So this model neglects those, but that model doesn't neglect that. And the road is here. Okay, this is the body of the car, and this is the tire of this one. Now I have a question. As long as you know the transfer function means TF, which is equal to YS over US. You remember that we have discussed in control problems, we have various inputs. You remember that? Now I wonder if you know the transfer function like this, and if you U is step, for example. It's a step function. I'm sorry. I want to make it red. If your input is step, what's the real life situation? That one, this one in real life In Turkey, I don't know the English name of it, but it's called kasis. Biriniz lügattan bir bakın bakalım. Kasis, bir dakika ben bakıyorum şimdi. Kasis İngilizce. Cached diyor. Cached. Bir okuyalım, dinleyelim bakalım nasılmış.
Cached.
Yeah, that's right.
Cached.
Duydunuz mu? Cached. Çıkıyoruz. Hemen yazayım şuraya. Cached. Biz Türkçe kasis deriz buna. Cached. So if that one is something like this, that means function u for that one is step. Okay. For this one, however, is u max sine omega t. Is a sinusoidal function. So as long as you know the transfer function, you can calculate the output. What kind of vibration you are going to feel inside the body by calculating Ys. Ys is equal to Tf times Us. Okay, so as long as you know the transfer function, you can obtain the vibration in your car as a result of either this kind of function or that kind of that represent that your vehicle is moving to a certain distance, for example, pavement part, and then stay over there. You see, this is a step action. That one is continuous vibration, or that kind of action might be. In Turkey we have a lot of one of those. Siliyorum önce bunu. Sonra göstereceğim şimdi. In Turkey we have a lot of one of those. Not step. One of those. So you are going, but you are bumped. You are having only one, bumping, not a continuous sinusoidal, only half of it. So we have a lot of, so that means you can calculate the vibration occurred here in the body itself by solving this one. First, giving this function as an input here, you can see that this is your input, okay? And if you give this input function, time function, then you can obtain the position, change of the position. Don't forget that. There is no force involving. These are all positions. Evet. Şimdi now we are approaching to the last. This is I'm not going to solve this one. This is also reflecting the similarities between the mechanical system and the electrical counterpart of it. Okay. Now that is the problem. In electric vehicle, we have a system like this. But be careful. Gear ratio N is defined here as the theta over theta m. This is an electric motor. Electric motor produces torque, and that torque rotates the system. So torque, bir dakika. O torku göstereyim ben. Yalnız çok ince çizmem lazım. 2 punto, 1 puntoya iniyorum. İndim. Kırmızı iyidir, kırmızı. Burada torque mechanical, torque electromechanical here. Neglecting the friction, so and also neglecting the losses here, you can derive the equations here. You can derive those equations, okay? The derivation of the equation might be theta. I'm sorry, niye ben kendi kalemimle yapmıyorum? Bir dakika. One transfer function is theta over, bakayım bu I mi V mi? Bir dakika. Gözüm görmüyor çocuklar. Çok küçük. EI. Evet, teta'nın da ne kadar berbat bir teta olduğu buradan görünüyor. Teta'dan kurtuluyorum. Theta over E input. Benim size verdiğimle uymuyor bu. Bir dakika çocuklar. I'm not happy about that one. That one is V. VA input voltage theta position. So this is my for today. This is my last slide. Now I'm going to upload another slide which we have to start. So you can also calculate this one as well. I don't know which one is going to be your home assignment. I'm not sure about this one. This is also important since this represents the electric vehicles system. In electric vehicle, of course, you have a battery plus power electronic device to control the electric machine, to control this voltage or frequency as well, and then electric machine model, you produce torque. There is only one gear, which is approximately 1 to 10 ratio. So the speed of 1 to 10 means that speed is reduced 1/10 over this. Electric machine speed is approximately 10,000 RPM. 10,000 RPM means approximately 1,000 radian per second in mechanical. So then we reduce the speed to 1,000 RPM revolution per minute, and then send it to the differential. Just wait a little bit, please. I think it's more than 1 hour I was teaching, so I'd better make a break. I better make a break here. So kaçta buluşalım? 45'te 11:45, tamam mı? 11:45. Eleven 45. Okay. I take a break. Now I'm starting again. Yes, we are starting again. Next week, we are going to start the transient and steady state response analysis of systems. For this part, we are going to look at RC and LR networks, electric networks, or mechanical friction inertia or friction mass networks. So that kind of networks are called first order systems. So we are going to look at the first order systems, and then we are going to continue the transfer function. When you solve this transfer function, by the way, when you solve it, you obtain this transfer function. So this is a typical first order transfer function. If you write the equations, for example, it's a simple, I'm going to write it, LDI dt plus Ri is equal, let's say, V, voltage. So current, when you solve this differential equation, it's a network like this. So this voltage, this is inductance, this is resistance. If you solve this, you obtain that, we already know that I is equal V over R, which is a steady state solution, 1 minus e to t over tau. Tau here was equal L over R, time constant. So the response of this one is going to be something like this. The current equation is this. Something like that. That one is current. That one is current, I, and that one is time. So if you come back this is the equation. V over R, 1 minus e to power t over tau. But time goes infinite. If time goes infinite, that becomes 0, and then your steady state value becomes V over R. That is the one. This is the one, steady state value. But time constant is important, since time constant tau is equal L over R. So if you increase inductance, your network becomes lazier, and then your value, your current rise becomes slower. But these are first order systems, and these are of course depends whether you have a step input. This is a step response, by the way, and that is your ramp response, and then this is a impulse response, and that is the second order system. You just remember, we have solved LCR network today. I just wanted to show you this one, and I'm going to leave it to Mohamed Said Hoja. He's going to give you some lecture on MATLAB. So that is the transfer function. You remember L over 1 over LC. You remember that differential equation for LCR network. It was 1 over LC over S square plus, şimdi hatırlayamadım ama burada 1 over LC vardı. Galiba burada da bakayım ne yapmıştık? Bir dakika, niye değişti bu ya? One over LC vardı. Burada da 11 R over L. R over L. Tamam. Böyleydi. S var önünde. Sorry. S. Tamam. Şimdi çocuklar, ben sizi Muhammed Seyit Hoca ile baş başa bırakıyorum. Hepinize iyi dersler diyorum. Yoklamayı aldım. Hatta çıkan 2-3 arkadaşınız da varsaydım. Yani yeni çıktılar onlar da, biliyorum çünkü. Hadi hepinize önümüzdeki hafta görüşmek üzere. Ödevi takip edin. Ödev veriyorum ona göre. Seyit, it's all yours. Senin çocuklar senin. Başlayabilirsin.
Teşekkürler hocam, sağ olun.
Para vermiştim çünkü.
Ha, tamamdır hocam, devam edelim biz de.
Kolay gelsin.
Sağ olun hocam, teşekkürler. Hello guys, everyone here? All right, let's start. Okay, everyone can see my screen now? Yeah, okay, let's start. So today we're gonna start with the DC motor modeling. We have a lab report here. I'm gonna share it later on. So let's start with our transfer function here. We're gonna create it in Simulink. All right, let's go our Simulink model. So first, let's check out our model here. As you can see, we have a armature resistance, armature inductance, torque constants, viscous friction gain, and we're gonna model this in our Simulink model. Here are our block diagram. So let's start it. First, we are gonna need inputs and outputs. Okay, we get one input and get another output. Okay, and then here in our model, we have an integrator for transfer function, divide function, and sum. We have a few gains, and we have a transfer function. Okay, let's add our transfer function to it. Okay, we add our transfer function, and then we need our sum. And we need a divide function. All right, so anything else we need? We need also a gain for a feedback. Then when you choose your parameters, the diagrams. Then we can start to create our transfer function. First, as you can see, our transfer function here, we got input. U is our voltage, input voltage for the DC motor. And before that, we have a subtraction and extraction for the feedback coming from our transfer function. Okay, let's start. You input and output. You can just Control C and Control V. You can just multiply how many you need. Let's say one input here. Our sum, we can also copy it and we can paste it here. But in our transfer function, the first one, the input, our input voltage is subtraction, and our feedback is extraction. So you can double click our sum and you can change it. The second one is to the minus. It will change it to extraction, all right? Just like this. And then we also have a gain. Take our transfer function feedback to the sum product, and you can just take it here. So in here, this feedback is like its direction is going to left. So you can change it by clicking, like right click. You can change format and just flip the block. It will just change its direction. So you just connect it with the dots. All right, so our transfer function is 0.01 s plus 0.5. So you just double click on your transfer function. Here your numerator is same, but the denominator 0.01, it was 0.01, you change it, and the second one is 0.5. And you just hit enter, it will change your transfer function is 0.01 s plus 0.5. So, and the second one is we have another gain here coming from our transfer function directly. So we just can copy this one and paste it. We want to flip this gain. You just go to format, flip your gain. We connect it. And then we have LA. LA, our armature resistance. It's going to input, output. You see, you get from all your output transfer function, this is your armature resistance. We just connect it to the LA, right? We can change the name also here. You just double click there and you change it to LA. All right. Then we just take it from here, you just connect it here, like you just choose this arrow and just connect it to the line here. It will just connect it. Also, we connect our transfer function to sum product. And let's change the names also here, don't forget it. Our U input voltage. And then when you double click it here, signal altimeters, you can see your input parameters here. So we just we're gonna define this input later on, and we give a value to it, like 100 volt. We're gonna use 100 volt in this experiment. And then let's continue with we have another sum product here. So we just here we can connect it with this. As you can see, we get the transfer function, we get the gain, and we multiply them, and then we add another sum product here. We're gonna get a feedback from the transfer function again, and we are subtracted, and then we divide this function, and then we get our output. Okay, we have a extraction, sum, and another extraction. So just double click it. Extraction plus extraction. You can add multiple sum and divide in here. Like you can change it from here. When you hit it, you get C3 input, one output from your sum. So the first, our gain and transfer function multiplied here and get the sum. So you just connect here. And the other one is our TL. can change the name of it. Then we have another gain from here. Right, but before that we have a divide and integrator. We have our divide function here. We can change it to let's say we change it. We're going to use our divide function. We're not going to use this one. So here we get our j, and it's divided by our transfer function till here. The transfer function times our gain, and then we divide it with j. Right. So you can change the the inputs. You can change it divide or the multiplication, both of them. So first one we're going to use our divide, and second one is the multiplication here. You can just change it from double clicking on it. Here we have our input j divided by our transfer function to here, right? So we just connect it here to multiplication and another input. We need another input. Here we call this j. So for now we connect till here, right? And then now we got our integrator. So we add it from our library. We got our integrator too. We connect it with the divide function. And on the output, we have a V torque constant. And then we are going to connect our, so you get connect here, your output, you can get another output here. You connect it, you can change it to remove it. And then our gain here, it was connected to some product, and you get your gain from here. The other gain also connected to here. So now let's check our system. Anything else? We got our inputs, we got our outputs. Yep. And we have another TA, armature inductance we get from the second gain. So we get another output from here. You get it from output to here. Let's check the name TA. We attend TA to here, armature inductance. Here our input voltage, KF and KA. So this one is, we attended to 0.05. This one is our feedback, it's 0.5. We attended, you just double click it and attend your gain value. Change the name to gain and KF. Then you can change, we can change the name to GTL. You can attend the name to your inputs, LATA. All right, so now we're okay here. So we have system, we have inputs and outputs. So now we want to see our outputs in a scope. So we just from the library you get the subsystem here, all right? Subsystem. We have a subsystem block. So you just do it like this. You just copy all your system, all right? And then you go your input subsystem, you clear it, and you just paste it here. Now the system you created in your subsystem, when you go back here, you just clear this. And then here, as you can see, your inputs and outputs are obtained here. You see, you can see your inputs and outputs. So here, you just can, when you click it, you can see your subsystems. Just like this subsystem, you can add multiple subsystem in your Simulink. So you can do with a more complicated system with the Simulink. So this one is just for basic one. So for this, we want to obtain our output, and we need input values also here. So from the library, we need a constant for attend the value to our input. We just choose a constant, and for the scope for the obtaining outputs, all right? And we get the outputs. So you can just multiply them. We need 3 outputs. You connect your output to your scope, and you can just copy the constant. We need 3 inputs, so you can just connect them. So when you click it, you can change the value. So the first one, or let's go to our okay, now we complete our circuit, our system. So now we're going to obtain our inputs. So here in our lab report, we said obtain U is the 100 volts. So let's change it to our U here. We change it U. And this one is 100 volt, all right? We attend it. And the second one, J is 0.05. Our J is here. Well, 0.05, all right. Then our TL torque 4. TL is 4. We change it to 4. So now our system is all right. Same stop time, you can change it to 1 or 10. End time, it says 1 second, so we can change it to 1 or 10, doesn't matter. So now your system is okay. You create a subsystem here for the DC motor. We have our armature resistance, armature inductance, we have our input voltage, we have our feedbacks. So now we just go our system, attain our inputs, and we're gonna obtain the outputs from the scopes. So let's just run it. So when you see, when you create your simulation and then you obtain your inputs, and then you get outputs from here, from the scopes, and you can see from the scopes. This is your torque constants. As you can see, your torque increased first, right? When you start the motor, and then it's constant. You go with the constant speed. Your DC motor is turning with the constant speed, right? So far so good, guys. Everyone following till here? So this was our DC motor modeling. So for the next week, we have a state space modeling. So just I'm gonna ask some question. I'm gonna give us some homeworks for the next week. So just take a look to steady state. Okay. Everyone here, guys? I'm gonna take an attendance list, so you can leave now. All right. Have a nice day, guys. See you next week.